There aren't any human settlements on the moon or Mars yet, but did you know that there are 7 people currently working and living on the International Space Station? And maybe someday soon we'll have astronauts living and working on the surfaces of other planets or going on deep space missions. There are a lot of science and engineering challenges to overcome to achieve this sci-fi dream of interplanetary civilization. And today we're talking with one amazing scientist who's working with her team to make this dream a reality. Hi, I'm Taylor from WowSTEM, and I'm here with Dr. Ariel Ekblaw. Hello. Who is the director of something called the MIT Space Exploration Initiative, and also the founder and CEO of the Ariel Institute. She leads a team of over 50 people who are all working together to develop the kinds of technologies and science we need to support human life in space. Hi, Dr. Ekblaw.
Hi, thanks for having me.
Yeah, thanks so much for talking with us today. I want to start by talking about the group you lead at MIT. What goals are you all working towards, and what kind of questions do you want to answer?
So I founded the group in 2016 to do 2 things. We wanted to democratize access to space, and so that meant walking around the Media Lab at MIT and finding different researchers from different backgrounds. So not just physicists like myself, but biologists, architects, artists, and designers, and showing them a pathway to participate in the future of space, really democratizing who gets to build and design this future. And then the second thing that we like to say we do is build, deploy, test, fly the artifacts of our sci-fi space future. So this is everything that goes inside of a habitat and would make a life worth living in space.
Wow, those are some really big, interesting questions. Yeah. I want to talk a little more specifically about the projects you've worked on, particularly your work on space architecture and something called the Tesserae platform.
Indeed.
What does Tesserae mean?
So Tesserae is a tortured acronym. I learned my lesson. I'll never do this quite long of an acronym again, but it stands for Tessellated Electromagnetic Space Structures for the Exploration of Reconfigurable Adaptive Environments. Really what that stands for is self-assembling tiles or pieces that can build themselves in orbit and reconfigure. We use powerful magnets on the edges of each of these parts to be able to transition between parts being drawn together with that force of magnetism, and then pulsing current through the magnets, neutralizing them and allowing the tiles or the parts to separate. And the name Tesserae, the reason it is such a tortured acronym, is that I was inspired by the small tiles in ancient Roman mosaics that make up a larger image. And they use this word tesserae for those tiny glass tiles. The idea being that, again, we want to be able to have this sense of modularity in space architecture. And so that's where the Tesserae name really comes from. And I fit the words, I fit the acronym to that word.
So you talked about how these buildings can self-assemble, basically. Can you talk a little bit more about what that means?
Yeah, absolutely. So this notion of self-assembly is actually a really big part of nature. So things like proteins self-assemble, or if you learned about DNA self-assembles. We are using this principle of different parts that are kind of jumbled together, and something wants to bring them together to form a larger structure. That's basically what self-assembly is. And in our case, the type of forces that we're using to bring those pieces together are magnets.
You also mentioned how this self-assembly works differently in different gravity. Can you expand on that?
Yeah, absolutely. So in a normal gravity environment, a 1G environment, which is what we call the gravity environment on Earth, these tiles would just stay on the countertop. They just stay on the floor, right? But when we're in a space environment in orbit, there's something called microgravity or zero gravity. This is when you're in orbit around a planet and you're essentially in what we call free fall. So to your human body, you're going to feel like you're floating. And outside of the habitat or outside of, wherever the humans may be observing, we would be trying to build the next generation of a space habitat out of these tesserae tiles that would be self-assembling because they're not having to fight the force of gravity. They're able to float in orbit, use that power of the magnetic fields to bring the tiles together, dock lots of different pieces, kind of like Legos coming together on their own in space, and then form a larger habitat or some type of closed structure.
So in the case of micro or zero gravities, in some sense, is it easier for these things to self-assemble?
Yes, exactly. So really, they only work this well in microgravity. It's something that's really special to the space environment. They would not be able to pop up off the ground and be able to self-assemble on their own in even a Martian gravity environment, which is about 1/3 the gravity of Earth.
So we've talked a lot about what it would be like in space or on another planet, but I want to know more about your experience with space exploration. Have you ever gone to space or been in zero gravity?
So I have been in zero gravity. I've had a chance to go 9 times on what we affectionately call the Vomit Comet. This is a plane, just like what you travel, between Kansas and Boston in, except it does what you'd want a plane never to do. It pitches really steeply upwards like this. The plane noses over, pitches really steeply downward. So it basically flies this arc in the sky, and then it repeats that 30 to 40 times, like a roller coaster in the sky. And so what this provides is if you've ever been on a roller coaster and you feel that motion when your stomach kind of lifts up, imagine that lasting for about 15 or 20 seconds over and over and over again. And this is how we test experiments. This is how NASA trains their astronauts. So almost all astronauts have gone through the Vomit Comet experience. And nowadays, there's anti-motion sickness medication that you can take, so people actually have a really wonderful time. There's no longer quite as much puking on the flight as there used to be. And it's really a core way how my 2 labs, the MIT lab and Aurelia Institute, the new startup, it's how we practice with our experiments before we actually take them to space. So I have had a chance to be in microgravity a few times. It's an absolute delight. And within our lifetimes, and certainly the lifetimes of those of you watching this video, we're actually expecting people like ourselves, day-to-day people who are not NASA astronauts, to actually get a chance to go to space. Things are really changing in the space industry, and within even just a few years, the costs will drop and more people will get a chance to go.
So I'm interested in the experiments that you run on the Vomit Comet, or what was the technical term?
The parabolic flight.
Parabolic flights. So you said that this happens every 20 seconds or so?
So we get 15 or 20 seconds every minute and a half or so. And in addition to floating, so you get that feeling like you're in a swimming pool, but without the pushback of the water. At the end of that, you actually get the feeling of twice your weight. So you're in hypergravity. So the plane alternates between microgravity and hypergravity. And the types of experiments, to answer your question, that we're doing are everything from science and engineering, like my tesserae tiles. We would call that an electromechanical experiment. We go from there all the way to art and design. People have designed performance spacesuits for doing a dance in zero-G, like a choreographed dance. We've had an amazing student and staff researcher who brought a painting kit and did watercolors in orbit, because anything with fluids and water is really fun to see in zero gravity. And so we've really run the gamut of very serious, rigorous science all the way through to architecture and engineering, to art and design, and even a little bit of philosophy and ethics for the future of human spaceflight.
Wow, that sounds really interdisciplinary. That's really exciting to see that combination of science and
That's
art.
Exactly the goal. That's exactly the goal. And it's also the spirit of the MIT Media Lab, where this first MIT lab was founded, is the importance of building a future for technology. Originally, the lab was founded very much with an Earth-based focus, but now we can also think about building the future of technology for space that actually welcomes people of all different backgrounds. You wouldn't want to live in a space habitat designed only by an engineer. It would look like this. It'd look like a science lab. But you also don't want to live in a space habitat designed only by an artist, because it needs to keep you alive. It is an extreme environment. And so I think the beauty of an interdisciplinary program like this, and for those of you studying many different things in school, is to keep alive that appreciation of many different domains of knowledge that are really important to humanity. So I am a physics major. I did really love my STEM degree, but I think there's a room and there's a place in space for space lawyers, space artists, space architects, all kinds of different fields.
Yeah, you mentioned microgravity and zero gravity. Can you expand a bit on what those concepts mean?
Yeah, absolutely. So microgravity is the technical term. That's because there are certain elements that keep it from the situation that we're defining from being exactly zero gravity. But most often you'll hear it called zero-G or zero gravity. To go a little bit deeper into why we don't always call it zero-G, Newton's laws remind us that there is no such thing as zero gravity. You will always be feeling some type of gravitational attraction to all kinds of different bodies in the universe. Right now, we're mostly feeling the gravity from Earth. And so the reason that we use the term microgravity is most of the time that we're able to feel 0G is because we're actually in free fall. And so that's what you're in when you're in orbit around a planet, you're in free fall. And when you're on the zero gravity vomit comet, you're in free fall as the plane is basically coming down off that arc. And so while we do feel the sensation of 0G, there is no such thing as zero gravity. So more technically, we call it microgravity. And there's a little bit of a difference between what we feel on the vomit comet when we're in these alternating periods of microgravity, hypergravity, normal gravity, and what an astronaut would feel when they're in orbit in space. It's much more consistent because they are moving around the Earth without those arcs in the sky like what we described for the plane.
I'd love to hear more about how you got to where you are today. Where did you grow up?
Sure. So I was born in California. My parents are both Air Force pilots, so I was born outside the Air Force Base. And my mom was one of the first female pilots in the Air Force. So a really big deal for me having this amazing female role model my entire life. And my dad was a fighter pilot. There's a long tradition of pilots going on to be astronauts. While they did not themselves, it really loomed large in my childhood. And so I got my start of loving space from growing up in California, and then in Connecticut, we moved back east, and really building on this experience that my parents had as pilots.
You seem like you've done some really cool things, but I know, at least for me, that there's always some bumps in the road along the way. Is there a time that you remember where things were really hard and you almost quit? And how did you deal with that?
I think it is really important when you hit challenges or times like that where you feel like you're struggling to know that you have it within yourself to persevere. Graduate school is a great example. It is a marathon, not a sprint. This can be a truism or something that feels very true in a lot of different aspects of your life. And so I think one of the techniques or a few of the techniques that I've used in the past is to know when to ask for help. Science is not done in a vacuum. Engineering is not done in a vacuum. And so knowing that you can learn a lot, not only from your mentors and teachers and professors, but also from your friends who are going through this learning process with you, that can be a really important support system, particularly in graduate school where you're trying to create new knowledge, but it's hard to do that all on your own. And then I think the other thing to think about is also having a sense of purpose can really help you through difficult times. So knowing that your work is important for something bigger than yourself is a great reminder that when you're struggling and you might want to give up, no, this is important. I'm doing something that is meaningful, and it gives you that sense of drive and purpose to continue forward.
Do you feel like you've always been this person really interested in science? Or do you feel like you had a lot of interests along the way?
I think I've had many different interests along the way. One of the things I loved about going to a liberal arts school for undergrad is I did study physics, but I also studied philosophy and history and language and literature. And so much of the richness of the human experience is to draw from both the humanities and from science. And so I've long had very crossover interests between those domains. And I think it's a wonderful thing to, if you are interested in multiple things, hold on to that. Don't let people talk you out of also being interested in history just because you're good at math. Or if you're good at history, don't write off math. You know, there's a wonderful mixing of different interests that can happen. And I think it keeps you a really curious and happy individual throughout your life if you can really foster those multiple different interests.
So finally, as we wrap some things up, I would love to hear about your big picture thoughts and imagining this field in 20 years, say. What do you hope or dream you and your team might be able to do with this technology?
I think it's a great question. Where will we be in 20 years? What are the big ideas in the field? One of the things I'm really working on, both at MIT and in a new startup that I just founded called the Ariel Institute, is how to scale humanity's presence in space. So right now, as you mentioned at the beginning, there are 7 astronauts on board the International Space Station. What would it look like to be able to support hundreds or thousands of people living and working every day in orbit? And to be able to do that, we need all kinds of infrastructure for space habitats, but we also need economics of a workforce. We need a sense of laws and customs for how you behave in space or how you don't behave in space. And so I think within 20 years, we're going to see this just explosion of positive explosion in a good way of new space stations in orbit that are not just government managed, but are actually independent companies running their own space stations. I think within 20 years, we'll see an interesting presence for humans on the surface of the moon. Some of you may know that we're going to send the first ever woman to the surface of the moon in this decade with the Artemis mission, the Artemis series of missions. And I think we'll have maybe just scratched the surface within 20 years of the first human mission to Mars.
Well, thank you so much for talking with us. I can't wait to hear more about what you and your team accomplish to help humans reaching for the stars.
Thank you so much for having me. It's been wonderful talking to WowSTEM, and I hope you all consider a career in space exploration. Thanks.